Okay, so now we will start our keynote talk section. And our keynote in this keynote section, the speaker is Professor Zhennan Wang. And Professor Zhennan Wang is a world-class expert in inverse problem and partial differential equations. And his research, including the mathematical images, and also applied to the real-world application. Also, Professor Zhennan Wang received some awards, including the academic award from the Ministry of Education and the Outstanding Research Award from NSTC. Okay, so it's a very is our great honor to invite the Professor Wang to deliver this lecture. Okay, so let's welcome.
All right, thank you so much for the kind introduction. And before beginning my presentation, I have to apologize to Daniel for not keeping my promise to speak in this session. And I was asked by the boss of TMS to speak in this session. So politically, I have to honor the boss' request. So I'm sorry. I take all the full responsibility for any trouble it may have caused. And this morning, I think a lot of people were listening to the talk by the primary speaker about machine learning. And I'm actually the follow-up work of his talk. In his talk, he mentioned something about DeepNet, and he also mentioned something about the cursor dimensionality. And today I'm going to give you different paradigms that will also beat the cursor dimensionality. But in addition, I hope my algorithm also honor partial differential equations. My goal is try to unbox the black boxes in the machine learning. So hopefully I can achieve my goal today in this afternoon. I know at the big lunch, people probably are quite sleepy right now. And hopefully I won't put you guys asleep. All right, so my talk is neural operators for the digital normal map. I will tell you what the digital normal map is later on. And so it's quite an applied problem. And this work is a joint work with Buin Kao. He's right now at Tamkang University, and Angela Asprey in Milano, and Elisa Francini from University of Florence. And this is the outline of my talk. I'm going to introduce the DM map, and also I'm to tell you how to approximate the so-called DM map, and then going to the introduction of neural operators. And before doing that, we give you some preliminary knowledge about this DM map, and then the actual construction of neural DM maps will be given in the section 5. So this is a medical problem called so-called electrical impedance tomography. So the goal is try to get the estimate of the conductivity function inside your body by injecting currents through electrodes attached on the surface of your body. All right. So once you put the current on the surface of your body, and then because our body is a conductive material, and the flow will flow into your body, and then you can measure the voltage on the surface of your body. And this is a typical non-destructive medical device. And from the current and voltage, this set of boundary measurements, you now get a knowledge of conductivity inside your body. Okay? And the pair of current and voltage are not independent. They are correlated through the partial differential equations. Because once you have current on the body of the surface, and then you basically solve a partial differential equations with the boundary condition, and then you can solve the equation. And from that equation, you can take the boundary value of that solution, and that will give you the voltage. So you have a current and voltage. And from this pair, you want to know the conductivity function inside your body. All right? So this is a typical applied problem. And mathematically, we can model this kind of problem by the very simple naive equation. This is so-called conductivity equation. It's a typical second-order elliptic equation. And the gamma here is just a conductivity function. All right, so given gamma and also given boundary condition, then you can uniquely determine a solution U. So you can construct the Neumann, the so-called conormal derivative of the solution. So now you have a map given gamma, then the map from h minus 1/2 to h minus 1/2. So it's a linear map. It's a linear map mapping from some Sobolev space to other Sobolev space. All right. So the so-called forward problem is to given conductivity function, and then you can determine the DM map. All right. This is a forward problem. So in elementary PDEs, I think people can solve this by the standard Lux-Milgram, and you can solve this the solution of this PDE, and then you can determine the so-called Dirichlet to Neumann map or Neumann to Dirichlet map. All right, but the most interesting problem is not the forward problem. We are actually interested in the inverse problem that we want to determine. We want to determine conductivity by knowing this DM map. So roughly speaking, we want to invert this operator lambda. We want to invert it. All right, and this is a typical inverse problem. Okay, so in some numerical reconstruction method, we actually want to evaluate this forward map. I mean, this lambda map from a given conductivity function to the DM map at each step. For example, if you consider Bayesian approach, and now from the prior of the conductivity function, you have the posterior distribution. So if you want to get an inference of the conductivity function, you want to run Markov-Chain Monte Carlo, right? And each step of MCMC algorithm, you have to evaluate this forward map, and then you get an estimate of new conductivity function at the next step, and then from that as a new conductivity function, and you evaluate the DM map. So every time you have to evaluate the forward map. This is the so-called MCMC approach, or you want to use a Kalman filter. The basic idea of Kalman filter is that you are given a set of data, and then you do the prediction by solving the partial differential equation, and you correct your prediction by your data. So you have a prediction, you have a correction, and in the prediction step, you have to solve the partial differential equation in order to get this DM map. And we know that in solving the PDE, we have a lot of methods: finite difference, finite elements, or spectral method. But in doing so, every time you have to, for example, in finite difference or finite elements, you have to do the mesh generation. And it takes time because for different conductivity function, you have to run everything once again, all right? So now the goal right now is to find a surrogate that can evaluate this forward map, the given conductivity function, and that will automatically give you the DM map. So in the sense that we want to construct a machine learning algorithm that will take conductivity function as an input function, and then through the machine learning algorithm, that will generate the DM map for you corresponding to this given conductivity function. All right. So this machine learning algorithm is like a factory. You are feed into some kind of meat, and that will give you a sausage. So this kind of factory is not only for chicken. Maybe you want to build the same factory for pork or for beef. and that will create the sausage. You are not going to build a different factory for different meats. Okay, so this is the idea. You want to have that kind of universality that will take all the connectivity function as an input. Okay, so this is the goal, and the goal is a little bit ambitious, but I'll tell you how to do this. All right, and this in this case. And the user machine learning algorithm learn mappings from finite dimensional space to finite dimension that Pims mentioned in this morning. All right. So you have a finite dimensional space to finite dimensional space. If the function is continuous, then you can learn it quite efficiently. All right, and you can also estimate all the parameters needed in this machine learning algorithm. But remember, here we have to learn a map. This is a big lambda map. It's a function space to a space of linear operators. All right, so this is an infinite dimension. And the range of this map is double infinite dimension. I say double infinite dimension because it's a linear map. Mapped from some software space to some software space. All right, so this is not something trivial. So how do you learn this kind of map? All right, and most importantly, you want to put this kind of mapping, this kind of a machine learning algorithm in computer. And computer certainly cannot learn infinite dimension things. All right, everything must be in finite dimension. All right, but this is not cheating. In order to achieve finite dimension, you got to have a good control how many dimensions you need in your computer. All right, and I'm going to go through this later on. Okay, and I want to emphasize that even though this DM map is a linear map, given a boundary data, and you solve the solution, that solution depends linearly on the data, right? So this map itself is linear, but from connectivity function to DM map is highly nonlinear. All right, this is so you cannot say that this map, this big lambda map depends linearly on the connectivity function. This is non-linearly. All right, even though the equation itself is linear, but this map is highly non-linear. So to learn this kind of highly non-linear map from infinite dimensional functional space to a space of linear operators is certainly not obvious. All right, okay. So there are three main goals in this talk. Hopefully I can achieve at least one of them. All right, I hope my machine learning models are interpretable in the sense that I want to construct my machine learning model based on my partial differential equations. All right, in this sense, there is no black boxes. Okay, so this is one of the main goals in my machine learning models. And second of all, I would like to derive the so-called universal approximation theorem, not just implicitly. I want to have a quantitative estimates in the sense that if I given a certain accuracy and I want to estimate the upper bounds of the layers, and also the size of neurons, how that layers and size of neurons depends on the accuracy. All right, so in this sense, once we have this kind of quantitative estimates, and we can observe that this kind of machine learning model will beat the curse of dimensionality. And I'll show you a little bit detail later on. And also, I want my machine learning model have the so-called discretization invariance, that I can train my model in a rough mesh. All right, and once I train my model, I determine all the coefficients in my machine learning model, and I can fit into a new connectivity function, which it evaluates a finite mesh without retrain my model. All right, and this is very important, because in training, if we train our model with the less number of meshes, it will be more efficient. but we want to use the same model to do prediction. So in this case, it is better that we can evaluate the function to a better accuracy. That means we want to have we want to evaluate a function in the final mesh. All right, but we can use the same model. Okay, that is the key. All right, and as I mentioned, this map, big lambda maps from an infinite dimensional space to an infinite dimensional space. So how do you learn this kind of map? All right, how do you learn this kind of map? So we know that we can only do finite dimensional things. We cannot do infinite dimension. Infinite dimension just in theory. All right, but if we really want to put our work at test, we have to somehow find a finite dimensional approximation to a nonlinear map. So how do you do this? So it turns out we can normalize the DM map. Now assume that a connectivity function is 1 near the boundary. Now I assume my boundary. Now my domain is a unit disk or unit ball, and the connectivity function is 1 near the boundary. So we can normalize the DM map. All right, and this lambda 1 is the DM map corresponding to the homogeneous connectivity 1. So you normalize this DM map. All right, it turns out even though this map, this DM map maps from H1/2 to H-1/2, but it is indeed a Hilbert-Schmidt operator. All right, you can show that this map is a Hilbert-Schmidt operator, and we know that from the very basic function analysis. I'm not sure whether it's basic or not, but from the elementary function analysis, you can approximate a Hilbert-Schmidt operator by a low rank approximation by choosing suitable basis. All right. So now I can use the Savary harmonics, because I consider a very simple case where domain is a unit disk, a unit ball, and then on the boundary of this unit disk, I can construct orthonormal basis. All right, by the Savary harmonics, and these Savary harmonics are eigenfunctions of Laplace Beltrami operator on the boundary. Okay, and for any given rank, J and H, then I can use this kind of a low rank approximation. All right, I do this kind of a basis expansion, and this is the base. All right, and then this is the coefficient corresponding to the normalized DM map. All right, and this is a finite rank approximation to the DM map. All right, it's nice, it's very nice, but we are mathematicians or applied mathematicians, and we want to see how many ranks we need in order to achieve certain accuracy, right? Because in my talk, I tell you I want to do the quantitative estimates. So qualitatively, I can have this kind of approximation, but quantitatively, I want to give an estimate of these ranks. Depends on the accuracy you need. All right. And this is the estimate. So you can achieve. Oops. So you can achieve the accuracy of epsilon by taking the rank in this relation. All right. So I can give you the estimates how many ranks you need in order to achieve the approximation of epsilon accuracy. Okay, and it turns out the rank you need is grows only polynomially in epsilon. So this is not exponentially. So even in this case, we do not have the cursor dimensionality. Okay, this is the first step. All right. So now we first do the surgery. We have to somehow find a good way to approximate the nonlinear map And this nonlinear map can be approximated by this low rank approximation with this kind of accuracy by using this kind of rank. So you have a relation. All right. So this is the first step. Okay. All right. So now this low rank approximation, you have this coefficient, and this guy is given because once you are given the harmonic function, the surface harmonic function on the surface, the basis is determined. So now you have to learn this coefficient. All right. And I denote this coefficient by CJK gamma. This is the coefficient we want to learn. Now we are now from infinite dimensional case to finite dimensional case, right? We have to learn this coefficient. And this coefficient is given by the inner products of these quantities. Okay? So now, if we denote this map from the conductivity function to the coefficients in this low rank approximation, this is a function, right? You have a function space from the real value. So this map gamma is a function. It's a function. And from the standard PDE, I would say standard, from the standard PDE, then you can show that this linear function, this is nonlinear function, I'm sorry. This is nonlinear function, is continuous. Okay? So now you have an infinite dimensional space, and the range is one dimensional. But this function is continuous. So now the question is, how do we learn a nonlinear function, a nonlinear continuous function effectively by the machine learning algorithm? Okay? And possible to DeepNet. I think you heard this in the primary talk this morning. And in this case, we do not need DeepNet. Deep means you have many layers. In our case, because the coefficient is a nonlinear function, so we only need one layer. So this is one layer, all right? And you can also consider this is a branches mentioned in the primary talk this morning. So we only need the branch net, and then you can approximate. There's a universal approximation theorem for this kind of nonlinear map. All right. So you can approximate this coefficient by this algorithm. This is a machine learning algorithm, and in this case, this coefficient are learnable. Learnable in the sense that you want to impose a loss function and you do optimization, and to find a suitable coefficients to approximate these coefficients. But you have to evaluate. You have to evaluate this conductivity at those points, and those points in their knowledge, in their terminology, they call those points are sensors. All right, that means you have to evaluate. First of all, you are given a function, and then you evaluate the function at those points. All right, and then you have the map. You have the output. The output of this algorithm will give you the approximation of the conductivity, the coefficient in this in the low rank approximation. All right, and you know that you had to choose the sensors beforehand, and sometimes you choose this sensor randomly. So now from the choice of these sensors, you know that those coefficients will depend on how you choose the sensors. Different sensors will give it different coefficient. That means different sensors will give it different machine learning model. So now this cannot achieve the third goal in my mind, because I want my machine learning algorithm, which is discretization invariant, does not depend on how you censor the input function. Okay, so this is something I want to avoid. And also, this another this is the you have the universal approximation theorem. This is okay. And as I mentioned previously, the learnable parameter depends on the choice of sensors. Okay. And lack of interpretability in the sense that this guy, you know, this guy is a nonlinear function, all right? Nonlinear continuous function. And you try to approximate this nonlinear continuous function by the DeepNet, by this machine learning network. What's it got to do with the partial differential equations? There is no partial differential equation involved in the construction of this machine learning algorithm. Okay, I know some people sitting here are very concerned about the connection of this machine learning model to partial differential equations. And this is a black box. In my opinion, this is a black box. Even though you know that this is a nonlinear continuous function, but that's the only thing you know. All right, and this has nothing to do with the partial differential equations. Okay, and also this is also a little bit about maybe we suffer from cursor dimensionality. Okay, and I will explain the cursor dimensionality in my on my next slides. There's a famous theorem by Yarosky back to 2017. He showed that for any map which is the k to the certain regularity, then there exists a ReLU neural network, choreograph A, that can approximate this continuous map within this kind of accuracy. But the depth you need is grows logarithmically. That it is okay. However, the size of neuron you need grows like this way. Okay, and M, what is M? M is the dimension of the input. All right, so if you look at our map mapping from infinite dimensional space to a real space, but we have to evaluate the input function, and in order to achieve the certain accuracy, you will increase the number of sensors, right? You will increase the number of sensors. That means the M will grow in terms of epsilon. So this term, this red one, will grow exponentially in epsilon. And this is a cursor dimensionality. Naively, without doing anything, we have this kind of cursor dimensionality. And once we have this kind of cursor dimensionality, it's very hard to implement this kind of algorithm in computer. All right? Your students will suffer. All right? Okay? All right, not me, okay? All right. So here's the new paradigm to overcome this cursor dimensionality, and also this kind of paradigm, this kind of machine learning model, we actually honor partial differential equations. It has a strong connection to partial differential equations. Okay, so this is a toy model. I'll give you a toy model. For example, you want to consider this integral operator, and you have an integral kernel. This is a convolution type. And now the input function is f. Given f, you want to compute this integral operator. Okay? And you can take the Fourier transform. You take the Fourier transform. The Fourier transform, this guy, just a multiplication. So this is input function, the Fourier transform input function, and you multiply by some quantity, and then take the inverse Fourier transform. Okay, so now remember what is the input function. The input function is f, and k is something maybe you know, maybe you do not know, but it really doesn't matter, right? You can consider this k hat as a learnable parameter. It can be learned by data. Okay, this is the key in machine learning. All right, so So now a single Fourier layer, this is a single Fourier layer. You input a function and then take in the Fourier transform and multiply some matrix and then take the inverse Fourier transform. And this kind of a single layer will be a approximator of this integral operator. And you do not need to know what the precise formula of this guy. Because once you have a whole set of data, and then you try to minimize the loss function between the data and the prediction, and that will give you a suitable parameters that will minimize the loss. And that suitable parameter is learned from that data. So this is a basic idea of the neural operator. Okay? And you can also put into several layers. Okay, this is deep. One is shallow, two is shallow, three is deep. In Chinese, we know one to a small quantity, but three, as long as three beyond, it's large, right? So this is multi-layer Fourier neural operators, and this is all kind of terminology about this. I'm gonna skip this. So roughly speaking, you wanna iterate your output from input function, and then you send the input function to the next layer, and the output of next layer will feed into the another layer. So this is a flow chart of this multi-layer Fourier neural operator. So given the function f, and through the first layer, and to the end layer, and then the output of this un plus 1 will be a good approximator of this kf. All right, this is a basic flow chart of this multi-layer FNOs. And there are several remarks I want to mention. This Fourier network does not depend on the fixed grid. The reason is that you are taking the integration. You are taking the integration. You are taking the Fourier transform of the function. All right. So basically, it is an integration. And how to do integration? You can do integration by any numerical integration. All right. And different integration will only give you a different error. All right, so this Fourier neural operator does not depend on the grids you used. Okay, so therefore this Fourier neural operator had the discretization invariant property. All right, second of all, it can do the so-called zero-shot super resolution. All right, so as I mentioned before, we train our model on a low resolution and directly applied the same model to a function who can evaluate on a higher resolution. And this is so-called zero-shot super resolution. But there's a caveat. There's no free lunch. All right, there's no free lunch. In order to train this model, you need a lot of data. Okay? So there's no free lunch. Without the whole set of data, you cannot train a good machine learning model. So once in a while, you have to be suffering, okay? Either begin or later, okay? And now I'm going to give you the construction of neural operator for the DMAP. Now I want to write out, this is a little bit partial differential equations. So this is the formula of this coefficients, okay? And then I can do the simple integration my parts, and that will give this formula. So in my talk, in all my theorem, I only need integration my parts, okay? And this is the only thing I know, okay? I can only do integration my parts, and Professor Liu can do better integration my parts, okay? All right. So now this is this VK is just a harmonic function with the Cephalic harmonics on the boundary, and this is given, right? We know this, and now you have another solution, Uj, which is the solution of the conductivity equation, but with the Sofronius harmonics as a boundary condition. All right. And you know that this gamma is an input function. So without doing anything, you cannot really learn this coefficient. All right. So, but there's a good thing. If gamma has a better regularity, for example, is a C2 function. Okay, then you can do this kind of transformation. You can transform the conductivity function to a Schrodinger equation with quite precise coefficients. Q is given by this quantity. Okay, so instead of constructing a solution for the conductivity equation, it amounts to construct a solution for this Schrodinger equation with the same boundary condition. Okay, and what is the advantage of doing this? Doing this because you can do this kind of iteration. All right, this is Schrodinger equation, and then with the source term, with the homogeneous boundary condition, and you can do this. You can solve this equation by iteration step. I only 5 minutes. Okay. Okay. All right. I'm gonna speed up. Okay, and then so you can decompose decompose into this coefficient into these two parts. All right, and this is the first part. First part, this is the input function, right? And then Vj dot gradient UK and gradient Vj dot gradient Vk. It's very complicated. All right, when you were a graduate student, you will compute this, right? But you don't need to. You let computers compute this for you. All right, and this is key in the machine learning. All right, the computer will never complain to you. Okay, it will only shut down and it will not complain to you. Okay, all right, and this is input. So now we have the basic model of the machine learning. All right, and then you can approximate that by the basis, but I'm gonna skip this. But the key is that if you have the certain regularity, you can estimate how many rank you need. Okay, and this is the key. That's why we can do quantitative estimates. I'm gonna go to the iterative step. This is the first coefficient in CJK. Okay, and then you do this kind of a little bit integration by parts. Then roughly speaking, you can solve the equation by iterative step, the so-called Picard iteration. And once you have Picard iteration, if you look at the Picard iteration, it's just a layer, right? Picard iteration, you are given the initial guess, and then you do this kind of iteration. And this is very similar to a layer structure in the machine learning. Okay, and then so I'm going to give you the you have the layer. So now you have this layer structure. You have a lifting layer. Given gamma, then you try to compute this quantity by auto differentiation, and then you have a certain hidden layer to do the estimate of CJK. And the projection layer will give you the coefficient in this in the low rank approximation of DM map. Okay, and this is a layer structure. I'm gonna so there are some remarks. The depth of the neural operator is different from the number of iterations. All right, but it's only maybe two times of the iteration steps, and then this all the coefficient you can learn at the ranks you need is can be estimated by the accuracy beforehand. And this coefficient can be computed independently, and also different JK have the different can also be computed independently. So you can make it parallel. Okay, as long as you have parallel computer, you can make it to the parallel. Okay, and this is the flow chart of the neural architecture. All right, and this is a quantitative approximation theory. Given the normalized DMF, you can find a new neural operator with the kind of layer estimate, and the layer of each neuron at each layer is a constant. So basically, you use this constant multiple number layer, so only grows logarithmic, so does not suffer from the cross dimensionality. And then this is an estimated rank you need to achieve the accuracy. Okay, and then you can apply this neural operator to some numerical method. And we do have some numerical simulations, but I don't have time to show you right now. So thank you so much.
Something like an integral kernel, right? But we don't have to know the detail of the integral kernel you said, because from the inverse Fourier transform of the data, right? Which means we don't have to know the transition matrix. You mean, right? We can. Uh-huh, uh-huh, uh-huh. Yeah. Mm-hmm. Okay, I got. Okay, something like this. Algerian, yeah, Algerian. In the page you said you want to normalize the lambda gamma, and you try to normalize it, and you write down lambda gamma hat equals to lambda gamma minus lambda one. And how do you know you need lambda one to normalize it? How do you know lambda one is the solution you want to normalize the gamma, the lambda gamma? And how do you know we choose lambda one? Yeah. Oh, okay.